from the GUI through this queue. Okay, this is going through the channel that is now in Project 3, Help Spring 18, has been there for a week and a half. Okay. Now you have to build over here a demo that's going to pull stuff out of the queue, the channel's queue, and I suggest you build a little dispatcher. To me, what I would do is I would have a unordered map whose key is a message attribute, and whose value is the callable object that does the processing necessary for that message attribute. And you say, what's a message attribute? What's coming? All that's coming. Okay, it's all coming, I promise. Today, at least a good part of it is today. So now what's all this other funny stuff? Well, graphical user interfaces, you don't want to build them in native C++. Can you? Yes. The only frameworks available for native C++ are clunky, archaic, old, ugly, awful, Qt, KDE on the Linux side, WX widgets, WX blocks. Bah. Okay. Can you build it? You can build an ugly interface, that isn't very flexible and can't do too much fairly quickly, and that's all you can do. But WPF, we'll see, is a very flexible, it's really a wonderful facility for building the graphical interface that you want. It's very malleable. It's easy to make it do what you want it to do. Extraordinarily easy to make it do what you want it to do, once you know a little bit about it. WPF uses two things. It uses markup. It's very like a browser model. It uses markup to lay things out, and then it uses event handlers to respond to events, which is just like in a browser, the markup is HTML, HTML5 maybe, and the events are being handled in JavaScript. In WPF, the markup is called XAML. It's very like, in some senses, like HTML. It's called XAML, Extensible Application Markup Language, and C# event handlers. Okay. And some of you are saying, oh, but I've never written any C#. This was really worrying me. And my response to you is, what you need to do, the syntax is close enough to C++ that the only thing you really need to know is understand a little bit about the object model behind C#, and then you won't have any trouble. I promise you, you'll be writing C# code in a day or two. Good C# code in a day or two. You'll be writing it in the first half hour. You'll be writing good. It won't take you long. But now we've got to communicate with this native C++, and C# can't do that easily. But what can is there's an intermediate language called C++ CLI, which is not C++. It's a .NET object model wrapped with C++ syntax. But it's a .NET object model. It's not this nice value type model that we're used to. Okay? It's a .NET model, meaning there are no copy constructors. You can't overload assignment operators. It's garbage collected. It has all the disadvantages of that. Okay? In my opinion, those are disadvantages. Not everybody agrees. But it has this overwhelming advantage that C++ CLI can talk to C# and it can talk to native C++. So it is a transformer. Think Pacific Rim, or whatever. Didn't ring a bell. You guys don't ever go to the movies? Anyway, it's a communication path to allow C# to talk with C++. I'm not going to tell you enough today so that you have any idea how to do that. I can start that conversation tomorrow in the help session a little bit if you want, but starting on Thursday, that's my job. So not starting Thursday next week, that's my job, because we're going to talk about sockets today, we're going to talk about socket code on Tuesday, although we'll look at we'll take a little quick peek today. And on Thursday, we're going to begin talking about WPF and C++ CLI. So I think you'll spend most of your time on Project 3 here, because here you're not going to do any, you're not doing any check-in, check-out. You're responding to a message that says, you say, I received a check-in message from the client, and you'll send back a reply, so the client can say, I received a reply to my check-in request. But no files are transferred, no version numbers are handled, nothing like that. It's just a simple, tiny little console application. Its purpose is to test that GUI and to test the channel. This channel, as it stands, will send files as well as messages. Right now, today, this instant, I'm going to show you before the class is over that it will. So this is where we're going. And there's a bunch of issues associated with the sockets behind this, okay, that are all handled by this code, but you know, for example, one of the on Piazza, one of the exchanges was, oh, I found this CPP HTTP client server, and there's a CPP HTTP client server that is synchronous message passing, synchronous. You're required to do asynchronous. Synchronous means you send a request and you wait for a reply. And if that takes a half hour for that reply to come, you wait for half an hour. That's the way HTTP works. So we really want to use, you don't want to use the CPP HTTP client server. I think they're useful. I like them. It's not totally done yet, you know. I posted it there because it is functional. I can talk to a browser using it. And, you know, maybe sometime Friday or something I'll give you a little demo of some of that. But I think what you want to use is the CPP comma file transfer. And this is in, again, Project 3 Help Spring 18, okay, right here. Right here. Okay, here's this link. CPCOM with file transfer. There it is. Oh, sorry about that. Yeah, let's go to HDMI. What is this guy? So let me go back. So, you know, click on this Project 3 Help Spring 18, and sure enough, CPP-COM with file transfer. Okay, cool. Now let's talk about sockets. One quick comment. So I already mentioned I've changed the order of the syllabus. I've already mentioned that the due date, I've extended the due date for Project 3 from April 3rd to April 10th, 1 week longer, meaning you have 1 week less to do Project 4, but you need that time to get your arms around WPF and C++ CLI. On Friday morning, there'll be a help session here, the normal kind of help session that I'll talk about the stuff we're talking about this morning and talk about Project 3 and so on. But Friday afternoon at 2 o'clock, I have a Phoenix meeting. I have taken this 4 midterms and I have combined it into a document that has reordered my solution. It's taken all 4 and put them together in one document and reordered them into questions with answers about object-oriented design, about Project 1 design, about Project 2 design, about syntax and semantics, about building extendable and reusable code, and threading models. Okay? So it's kind of a topic-oriented, you know, in-order presentation, and even if you did well, you know, probably wouldn't be a bad idea to go take a look at it. Just, you know, I think it, again, a good way to prepare for an interview. But for anybody that got less than an 85, you're invited to come at 2 o'clock to this room, and we'll talk a little bit about this. I'll talk a little bit about the midterm makeup, and we'll talk about trying to get yourself reoriented. How do I dig myself out of this hole that I got into? Okay, so. Okay, now with that, let's talk about sockets. Okay, so Win32 sockets. So what are they? In the early days, there were a whole bunch of different network protocols. Microsoft had their own version. I'm trying to dig out of my memory what they called it. NetBUI, I think, is what the original. And IBM, Token Ring, and blah 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 blah. And so the different networks, there were a whole bunch of protocols available, and the network programming for each protocol was different. So sockets were invented, I believe, in Berkeley. They were the socket specification, and the first demonstration was in Berkeley's BSD, their version of Unix. So that provided an interface, a common programming interface for all those different protocols. Now, it turns out these days almost all networks use TCPIP. There's only really one, okay? But still, it's a higher level than TCPIP. Not a whole lot higher. It's a low-level protocol. Not a whole lot, but it takes care of some details for you. So sockets provide this common interface, allow you to establish connections between machines to send and receive data. We're going to talk about connected socket streams. There are other flavors. For example, there's UDP sockets that send broadcasts to a set of designated receivers and do no error checking. Message gets there or doesn't get there. IP doesn't, datagram, they don't care. But it's fast, quick, good for games, good for video display. If you drop a packet in video display, you see transiently for about a half a second a little tiny dot on your screen, okay, that shouldn't be there. Gone away. Okay, so it doesn't matter. But if we're sending communication like we're doing messages, it's really important. So we want more than datagrams, and we'll talk about that in just a second. And sockets support simultaneous connection of multiple clients to a single server machine, and we'll see how that happens in this lecture. So for those of you who might not have taken a network course, here's a 30-second description of your 30-second network course. Okay. So IP is a routable protocol. It sends packets to a designated destination. The packet contains the destination address. And the intent is that packet goes from network to network to network to network through a bunch of hosts. And through a bunch of hosts and backbones. So a network is connected through a backbone to another network, connected to another network through a backbone, and so on. And the packet is just progressing through that chain. And routers are smart enough that they say, they'll send messages here, and then they say, oh, that's getting congested, I'll send them this way. And what that means is that IP messages may arrive at the destination in a different order than they were sent, because some of them may be going through different paths. What I consider to be a message might be 24 IP packets. 13 of them went this way, and the 11 went that way, if my arithmetic is correct. Okay? I can't do arithmetic after 10 o'clock in the morning, and I don't do very well before then either. So, but so you know, they are very likely to arrive out of order. And if a packet is dropped, IP doesn't care. So what? Gone. But layered on top of that is transport control protocol, and what that does is three things. One is that it makes sure that messages are presented to the receiving machine in the order they were sent. And the second thing it does is that if a message doesn't arrive, the sender will know it. Doesn't guarantee that the message arrives, it just guarantees that the sender will know it. And there's a retry mechanism. What happens is if there's a sequence and this message doesn't come within a timeout period, then before presenting it to the client, to the receiver program, it sends a message back to the sender. I didn't get this packet 53, and so this retry mechanism happens. And eventually it may, it may come or it may not. If it doesn't, then the sender knows that it didn't. Usually it doesn't because the network connection broke. Somebody pulled the plug, maybe. And the third thing it does is flow control. So TCP works hard not to flood the receiver with bytes. Receiver may be a server that's very heavily overloaded and can't handle too many, and so this flow control throttles the sender back to send at a much lower rate so he doesn't overwhelm the receiver with data. Okay? So TCP ensures correct order, ensures that the receiver will know if a packet doesn't get received, and manages flow control to avoid overwhelming the receiver. That's your 30-second tour of networks. Okay. So we're going to talk about TCP/IP-based sockets, connected sockets. Connection-oriented means that the two communicating machines must first connect. One has to have a listener that's listening, waiting for connection requests, and the other one sends a connection request. And we'll see a little later on this morning how that actually happens. All data is sent, is received in the same order because it's based on TCP. And streams mean that as far as the sockets are concerned, the only data is bytes of data. It doesn't know about strings, it doesn't know about doubles, it doesn't know about ints, it doesn't know about widgets, it doesn't know about vectors. All it knows about are byte, 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 byte. Low-level stuff. Okay? One of the things, if you look around the web a little bit, you'll see people say, help me, help me, help me, help me. I designed this socket application and it worked just fine at home, and I took it into work and it doesn't work at all. Sockets are buggy. And the reason is that sockets just know about bytes. So this guy had this notion of a string he's sending or some message he's sending, and the server at home was so lightly loaded that it gobbled that up right away as soon as he sent it. So he sends it, gobbles it up, sends it up, it gobbles it up. But when he takes it into work, the server is more heavily loaded, and it gets a quarter of the way through the first message and stops while he's sending more stuff. The next time it gobbles up, it gets the second, the rest of the message and 20% of the next message, and it's all garbled up. You have to frame messages. If you want to use sockets, you've got to frame messages. So all these people, help me, help me, help me, they're not framing messages. It's one of several problems. Okay, so if you remember anything about this lecture, this diagram I want you to remember. So each end has a receive buffer. So sockets are bilateral. You can send and receive on the same connection. We're not going to use them that way for reasons I'll talk about in a minute. Browsers use it this way. And my CPP, HTTP client and server uses it bilateral, okay? But what we're going to use, the COM with file transfer, doesn't, and I'll explain why in a couple of minutes. But what happens is, let's suppose I'm sitting here on the receiver end and I call receive. The receive function, I tell it I want to receive 23 bytes. How do I know that I should receive 23 bytes? I have no idea what the client sent. We got to do message framing, okay? So we'll get to that. But I say I want to receive 23 bytes. If there's 23 bytes in this buffer, it comes back with 23 bytes. If there's 13 bytes in this buffer, it comes back with 13, and it tells me I read 13 bytes. And it's up to your code to make sure the rest of the bytes get pulled out. So you got to sit here in a loop. Keep trying until you get all the bytes that you wanted. And you say, oh, I got to write some code. My socket library takes care of that for you. Okay? So if it has all the bytes I want, I come away with all the bytes. If it has part of the bytes I want, I come away with part of those bytes. If it's empty and I call receive, I'll block. I'll block until the receiver, until the sender puts some bytes in that buffer. If the sender never puts any bytes, I'll block forever. Now let's talk about sending. So I say send 23. If there's 23 available spaces here, I send 23 and I come back. If there are 13 spaces available, I send 13 and I come back saying I sent 13. And it's up to your code to make sure you keep trying to send the rest of those bytes. Okay. So if there's room in the message for everything I want to send, it just sends and I'm done. If there's some room but not enough, it fills up the buffer and then returns telling you how many it sent. If the buffer is full, it blocks. And it blocks until this guy pulls out some bytes out of that with a receive out of that buffer. Okay? If he never does, it blocks forever. Okay. Socket connections are based on domains, IP4 or IP6. The socket library that I've given you in Project 3 Help Spring 18 handles both IP4 and IP6. I'm only going to talk about IP4 because IP4 is significantly simpler. One little tiny part of it is significantly simpler. But the library handles both. You don't need to use the library directly. If you use the channel already has that library embedded in it. But we're going to look at the library a little bit just to see how it works on Tuesday. It has a type, stream or datagram, and stream, we're going to use streams because we want to connect it. We want the TCP. We want things to come in the right order. We want to receive them in the order they were sent. We want to know if something we sent wasn't received, and so on. And there's a protocol, TCP or UDP, which is very close to, very close correlation between those two. And when we create a socket, basically this is a platform API, Windows or Linux or whatever. And we describe the domain, and we describe the type. And this is a flag. You can tell it that I want asynchronous sockets. Don't do it. Okay, I handle all that processing, all the asynchrony for you. Sockets, Microsoft sockets, asynchronous sockets for years were buggy. I believe now they work correctly. But they're a little complicated. I think it's much easier just to do it the way I'm doing it. I handle the asynchrony. I don't want Microsoft handling my asynchrony. I really don't. Okay, I'm going to handle it. So I do. Okay. So connecting sockets. So now we have a socket address. This is an IP4 address, and it's quite simple. Okay, you know, just the domain, and here's the address. You know, the dotted quad 127.0.0.1, and a port. And what happens is the model of sockets is an address that designates a machine, and a port designates a service, an application running on that machine. So, for example, port 80 designates the standard web server unsecured HTTP, standard HTTP service. Port 443 represents HTTPS, secure sockets layer HTTP. Okay, and there's a ton of others that are already allocated, and then other new applications will define them. The one thing about sockets that you have to understand is that if a listener is listening on a particular point, you can only have one listener on a given port on a specified machine. One machine can only have one listener on each port. You can have an arbitrary number of listeners, but I can only have one on each port, because the model is that port represents a service, and a listener, if I have two listeners on it, it means I have two services using that same port. Doesn't make sense. Okay. There's some applications where it does, and you know, people do some fancy footwork to get around that. But the server listener binds to a network card using an address and a port. Okay, and a typical machine might have more than one IP address, by the way. This laptop has 3. It has an IP address that my network gives to me. It has an IP address for VirtualBox, virtual machine. It has an IP address for VMware's player, virtual machine. Okay, so you can have an arbitrary number of IP addresses, but and a machine might have several network cards. You know, if I'm a server in a rack of servers somewhere in Amazon, I probably got 7 or 8 or 10 or 16 or something network cards in that one machine. Okay, just to scale out. Okay, and then I connect. And so I give it a socket. So I've created a socket, I give it a socket, and I give it a socket address and the size of the address, and away I go. So a transaction looks something like this: client-server processing. Server creates a socket, client creates a socket, server binds, server calls listen, but bind associates it with a network card, but a listen puts it in listen mode, but it doesn't start the listener. The listener doesn't start until it calls accept, and that's a blocking call. When accept returns when there is a connection, and it returns with a new socket, not the socket he was listening on, a new socket, and what he's going to do, the listener will create a thread, hand that thread that new socket, and that thread will talk to the client, and the listener will go back to listening. So we have high availability for the listener. And then, that thread does send and receive with the client, blah, 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 and eventually will shut down and close. To use the sockets library, you need to #include winsock2. And if you're going to use C++ 11 threads, you need to #include threads. And you need to tell the linker that you're going to use the winsock32.dll. Winsock32.lib, I guess DLL, that's what they call it. But anyway, there's also a pragma that you can use. And if I remember, I'll show you how, instead of putting it here in this property page for the project, you can, in your source code, you can put a pragma that tells the linker, the builder, that you need to talk to that. So the sockets API, so all of this is Berkeley sockets. Standard, and everybody recognizes this. Macs recognize it, Linux recognizes it. So I can communicate back and forth between these various platforms using sockets really easily. This is Windows specific for startup and shutdown. And what this does is this loads if the WinSock32 DLL isn't currently loaded in memory, it loads it. And it does a reference counting scheme. This will unload it if the reference count goes to 0. Okay. It'll decrement the reference count, and then if that decremented reference count is 0, it'll call unload library, and unload it, but otherwise it doesn't. And then, you know, socket, connect, bind, listen, accept, send, receive, shut down, and close socket. And you want to do it in this order. You want to shut down first before you close the socket. It turns out that if you never call shut down, the way I wrote my code, it'll work. But this is helps promote a graceful shutdown. Shutdown sends a socket message to the other end saying, I am no longer going to send you messages, or I'm no longer going to receive your messages, or I'm no longer going to talk to you. I'm no longer going to talk to you nor listen to you. We're getting divorced. Okay. So, all right. So here's the server sequence, you know, in the right order. So here, there should be a shutdown here. This shutdown is shutting down the listener socket. This shutdown, I left off there should be a shutdown before I close the socket. This is the socket that the listener ended up. Okay, so. And now there's a series of, you know, for each of these, I've got a little bit of, you know, a little more detail about the, not many words, but, you know, you can see the data that's coming in and coming out and what you're doing. Let's look at, here's the accept function, and notice that the accept function returns a socket. Okay, this is the socket that accept is listening on. This is the socket that it returns that the client's going to talk to. Here's the way this works. So the client has to know the listener endpoint, is IP address and its port, the listening port, the port that this listener is listening on. And so he sends a connection request, and that makes this guy return from accept with a new socket, not the listening socket, a new socket. He creates a thread with that new socket, and that new socket starts to talk to the client back and forth, and maybe the socket is just pulling out messages, as we'll see a little later on, just pulling out messages and dropping them into a queue to be processed in the server somewhere. Okay? So now this client can say, remote endpoint, tell me your IP address and port. And the IP address is useful, but the port is of no use whatsoever because you can't connect to that port. It isn't the listening port. So if I want my receiver, if I want the server to be able to reply to me after the connection is broken, and we will, it's the way my communication channels work, I've got to send not only the address, I got to have in my message not only the address where I want it to go, but my address is a return address. That little thing in the upper left corner of the envelope, okay, that's telling the server, here's how you reply to me, because it has both my IP address and my port number that I'm going to listen on. So now I can have an arbitrary number of threads sitting here talking to different clients. So one server can have multiple concurrent clients, blah, 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 blah. Away you go. Okay. Here is receive. So notice I said, I want to receive this many bytes. And receive says, here's how many I gave you. And they can be different. and your code has to take care of it, which my library does, so your code doesn't have to take care of it. Okay? Has to be a while loop, you know, counting those bytes. And here is send, same thing. Here's how many bytes I want you to send. Sender says, here's how many bytes I actually sent. And if they're different, you got to write code to pump in some more bytes. And again, good news is your code doesn't have to, okay, because my code already did it. Shutdown, you can tell them, I'm not going to send you any more messages, or I'm not going to talk to you anymore, I'm not going to listen to you anymore, I'm not going to talk to or listen to you anymore. Okay. This is where we have an argument. Here's where we get divorced. Okay. So okay. And closed socket, you know, now that does clean up. A socket is a kernel object, has a little bit of memory associated with it, and a closed socket is necessary in order to clean that up. This is one place where the Microsoft API is different from Berkeley. Berkeley, I believe, is just close, but Windows is closed socket. And WSA cleanup, you know, blah, 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 blah. So there's a sequence of client code, you know, WSA startup socket, resolve the address and connect. Send, now I send and receive. I shut down, I close the socket, and I clean up. And in one process, you can call WSA startup and shut down multiple times. It does no harm. It's reference counted. You know, doesn't really do anything. So long, for every startup, you have to have a shutdown, or the library may never get unloaded. But so IP addresses, you know, I'm not going to talk much about. I'm going to kind of skip over some of this. Here's a connect function. This tells me whether this connection succeeded or not. This is the socket. This is my socket that I want to send on. Okay. And this is the address that I want you to connect to. And name length is just the length of the socket address. In this world, there are two kinds of platforms, Bigendian and Littleendian. And Bigendianness or Littleendianness depends on the order of bytes in an integer. Some put the high order byte first, some put it second. The whole world does it one way, I think Bigendian, and Microsoft does it the other way, Littleendian. Okay, it could be the other way around. You know, given a binary choice, I have a 50-50 chance of getting it wrong. Okay, so it may be that Windows is Bigendian, but anyway, doesn't matter. I don't have to worry about this if I talk Linux to Linux or Mac to Mac or Linux to Mac, because they're the same Indianness. But if I want to talk Windows to any of the others, I got to use these functions to convert the order. And what this stands for is host to network. Network is Bigendian, and this is for shorts, and this is for longs. Network to host shorts, network to host long. Okay, so. Okay. A word of caution, with stream-oriented sockets, send does not guarantee transfer of all bytes. That's why send returns an int. It's up to you to ensure that all bytes are actually sent. My library does that for you. With socket communication, so here's a communication channel using sockets, and we know it can block. It can block on the sending end, it can block on the receiving end, depending on the state of the buffer. If I want to send and the receive buffer is full, I block. If I want to receive and and my receive buffer is empty, this guy hasn't filled it, then I'll block. So I use a send thread and a receive thread to prevent that. These threads can block just fine because all they have to do is to push messages into the socket and pull messages out of the socket. That's the only thing they have to do. So if there isn't a message, it doesn't matter if they're blocked. But I don't want to block this guy out here. I want this guy to be able to construct a message, put it in the queue, construct another, put it in the queue, do whatever he wants to do. Whenever he wants to construct a message, he puts it in the queue. And by putting it in the queue, he just calls post message and then puts it in the queue. This guy is pumping messages into this queue, and this guy out here is just calling get message. And if he wants to, he can look at the queue and see if the queue size is 0 or not. If it's 0, and he doesn't want to block, he won't call get message. Okay, but otherwise he does. There's another issue. That's talk protocol. So we know that a socket can have a bilateral connection, and what do you think happens if both ends talk? What happens if both ends talk? Deadlock. Both buffers full, they both block. Because the buffers are full, nothing can happen. What happens if they both listen? Deadlock, because both buffers are empty. They're both blocked on empty buffers. So you got to have some sort of protocol. Now we are going to use a one-way protocol. I'm going to talk about it in just a second. Okay, but not on the next slide. I'm going to talk about it in 5 seconds, in 5 minutes. Okay, I can do this. If I create a talk token, and for any given channel make sure that there's only one token, then if you hold the talk token, you can talk. Otherwise, you listen. So, and I give the talk token to the connector. The listener doesn't have it. The connector does. So the connector is required to start talking. And he says, talk, 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 send, send, send. This guy's received, blah, 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 blah. And then he sends a talk token. Talk token comes up. When he sends a talk token, he converts to receiving. And when this guy gets the talk token, he converts to sending. And so now this guy's got a piece of cake, works like a charm. I've used it once or twice. It works just fine. There's other ways of doing it. Now, which I'm going to talk about in a couple of minutes. Another issue is message length. How does the receiver know how long the message is? He doesn't. How do you know? You don't. So what do? You got to frame messages. There has to be some way to tell that the message has ended. You can do that with XML. Angle bracket, message, angle bracket, blah, 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 angle bracket slash message, angle bracket. And you keep, as you're pulling bytes out of the socket, you keep looking for that terminator. So anytime you see a closing angle bracket, you're looking at the back end of the string. Every time you see a closing angle bracket, you start moving up the string to see if there's a slash message angle bracket. And if there is, you're done. You got the whole message. But there's other ways. A way I think is better. I'm going to choose to use an HTTP style message. I'm not going to do HTTP processing because I don't want it asynchronous, send and wait for a request. But I'm going to use an HTTP style message. We'll see that in just a second. So we do need to do message framing, and that's what that says. Okay, so I didn't talk about UDP, didn't talk about socket select, didn't talk about non-blocking sockets. We don't need any of those. If you're around this summer and you're bored and you want something to work on, be my guest. There's lots of good stuff to look at. Extend my socket library to handle UDP. Okay, so now I want to look at a diagram to try to get everything really clear. Here's my model of a communication channel. All one way. So sockets we know are bilateral, but I'm not going to use the bilateralness. I'm just going to use them one way. Here's a socket connection, here's a socket connection, here's a socket connection. These are all, from a communication point of view, these are all peers. The communication structure are identical. Each one has a sender and a receiver. They each have a listener. They each have a sender. And so, you know, this guy wants to send, he just sends, and it doesn't matter whether this guy is already talking to somebody else. It doesn't matter. He's got a queue, and I just keep pumping messages into the queue. Absolutely can have multiple concurrent clients. The sender only talks to one at a time, okay? But if you've designed your channel well, which my channel does, you do a little bit of message inspection. So in comes a message for you to send, and you inspect it. And you say, is the endpoint the same one that I last sent to? If the answer is yes, you just send it. If the answer is no, you close the connection, and you open a connection to the new endpoint. Piece of cake. So now, all these guys have to do is configure a message that says, here's where I want it to go, and by the way, if you want to reply to me, here's my reply address. Done deed. Piece of cake. And now, this is a flow system. It all flows really naturally. Nobody, there's no waiting here at all. Nobody waits for a reply, ever. Ever. As far as the communication channel is concerned. This diagram explains a little bit about how that happens, but before we look at it, let's look at messages. So I say HTTP style messages. So we're not going to use the HTTP protocol because we are not going to synchronously wait for a reply. But we're going to use a message structure very like HTTP messages. Now HTTP messages, genuine HTTP messages, have a standard set of commands. Get, put, post, delete, head, trace. There may be one or two others. I don't remember. Which we might choose to use or might not. But HTTP messages have a whole series of lines. Each one of these is a line. Okay? Those are attributes in a header, and they are each. There's text and a new line, text and a new line, text and a new line. And the message signals to the receiver that with two new lines in a row, a blank line, that this is the end of my headers. Okay? Now, if I want to send a, so the socket's just sitting here, read line, read line, read line, read line, read line, empty line, headers are done. And if I haven't seen a content length, I know my message, I'm done, I return. But if I see content length equals some number, I know that means that there's going to be some bytes, some binary bytes in the message for me to pull out. And so I just go receive 35430, bam! Or whatever the length is. So now I can send binary data, piece of cake, you know, and there's no issue. There could be lines and new lines here. Who cares? Because I'm not looking at lines. I'm not reading this as lines. I'm reading that out as one block. Bang. Okay. So now, here's how this communication channel works. This is COM with file transfer. What I put in your Project 3 Help Spring 18. So here's a client, and he prepares a message, and he puts it in this queue. And this send thread, what he does is he looks at the message to see where it's going, and if he's already got a connection open there, he just sends it. If he doesn't, he closes a connection and opens a new connection, okay, and stuffs it in the socket. At the receiving end, this thread, this client handler thread, is pulling bytes out of this. He's reading strings out of the socket. There is a string, receive string function in my library designed just for this application. And so he reads an attribute, and the attributes are all key value pairs. Key, colon, value, exactly that format. So, you know, content length, colon, value. So he just pulls them out, and he's building up a message, and if there's no buffer of bytes, he just puts it in the queue, he's done. But if there's bytes in there, that message has probably told him this is a file coming in. Okay, and so what he does is he opens a file, and he writes that chunk in. Next message comes up, writes another chunk in, writes another chunk in, writes another chunk in, until finally he gets a chunk that is less than the size he's been receiving, the chunk size, could be 0. But then he writes that smaller message, maybe 0, and closes the file, and then, and only then, he puts a message in here in this queue that says, you got a message, you got a file, okay? Bing, 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 you got a file, okay? So, piece of cake. And you say, that's too complicated, it can't possibly work. Message, 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 message. Notice I got 2 clients, and if you look carefully at the output, the clients are getting replies to the message they've sent. And here, I'm sending logger.h, and I'm sending logger.cpp, and now I received logger.cpp, and I received logger.h. Piece of cake. Works just like that diagram. On Friday, we can look at this a little bit if you want. You know, I think probably on Friday it would make sense to look at the Project 4. For you guys who came in late, Project 4 due date has been extended 1 week. Project 3. So, no, Project 3. Project 3. Project 4 has not been extended. Project 2 hasn't changed, obviously. Project 3 has been extended 1 week, meaning you have less time to do Project 4. But remember this diagram. So, this channel, that's what I just ran. It's in Project 3 Help Spring 18. You know, for you guys who are sending messages back and forth on Piazza saying, you know, how do I get started with sockets? Oh, here's a good reference. Oh, go look at that, or go look at this. No message framing, no talk protocol, no message structure. You know, you want to do it, be my guest. If you want, somebody want to use CPP, HTTP client and server, that's synchronous, not asynchronous. You're required to have asynchronous communication. So you want to do that, be my guest, but you'll be done in July. So if you use the channel, then you know your job, as far as the communication goes, is to build a little, you know, tiny little console application that is pulling messages out of these queues and dispatching them. And again, I would have a map that takes an attribute, you know, a message ID, and calls some processing appropriate for that message. And for Project 3, it's just going to say, I received a check-in message. I received a checkout message. I received a whatever. And sends back a message that says, the client says, I received from the server notification he got my message, or something. Okay? That's all you got to do to satisfy that part of Project 3. Now, here, you got to wrap your arms around WPF, Windows Presentation Foundation, which is an excellent, excellent, excellent GUI framework, and C++ CLI, because this is managed code, this is native code, this is a translator between managed and native code. The syntax is like C++, but it isn't C++. It's a .NET model, .NET object model, meaning no copy constructor, can't overload the assignment operator. Managed, managed object lifetime, garbage collected, blah, 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 blah. It's C# written in C++ syntax. It's C# written in C++ syntax. So why don't I just build it in C++? Because there are no good GUI frameworks written for native code. There is one good one, but it's very complicated. It's used by professional video developers. The people who write those fancy displays on TV, you see the news come on and really fancy graphics and all, that's done with C++. That's done with an application called Cinder. And if you want to spend all summer long figuring out how to do it, you'll be able to do absolutely terrific stuff. Great summer project, but we don't have the time for that. WPF is absolutely terrific, but you got to do C#, and you say, I don't know C#. We're just talking about C++. That's not fair, and you'll discover that. You'll look at it and you'll say, oh, I can read that. That syntax makes sense to me. Even if it's C#, it looks a lot like C++. The object models are different. You have to be aware of that. And we'll talk about that. When I talk about C++, CLI, and WPF, I'll talk about that. So, but your job, most of your time in Project 3, you're going to spend here. This is, I think, an afternoon. You pull that out, you write this, write a little dispatcher, and you'll have a little console application here. This just sends blip, 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 blip messages. Now you'll build a GUI that has a check-in pane, check-out pane, and a check-in button. And when you click that button, you're not checking anything in. You're sending a little message going over this channel. This goes into patch. I received a check-in message. Okay? So the closer you make this, you're not required to send all the information necessary for check-in from that view. Wouldn't be a bad idea to send it, because now you have less to do for Project 4. And as of today, you have less time for Project 4 than you did before, 1 week less, because you have 1 week more. Because it's going to take us a little while to talk about this enough so that you know how to do this. That's where we're going, baby. So we can start this conversation tomorrow, 9 o'clock. And again, for anybody that came in late, I have the Friday morning, we're going to, it's a continuation this morning and talking about Project 3. But in the afternoon at 2 o'clock, I'm going to have this meeting for anybody that didn't do well with their midterm, and we'll talk. You can't see that. You fell down on the job, Nog. You didn't. So this is just a document that pulled all 4 midterms together and ordered them in a rational order. Okay, put all the things in current, topic, 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 all the questions in this topic, all the questions in this topic, all the, and we'll talk about that at 2 o'clock, and we'll talk about doing midterm makeups at 2 o'clock. And if you got 85 or above, you don't need to come to that meeting, and you probably shouldn't, because otherwise we'll overflow the room. You can come if you want, and what will happen is if we overflow the room, I'll say, who got higher than 85? And be honest. And I'll say, okay, all you guys leave. Okay, but that's what we're going to do. Let's take a little peek. We got a little time, so let's take a little peek at, let's see where I am. Let's take a little peek at the sockets part of this. So in the HTTP client and server, I'm sorry, in the in the COM with file transfer, CPP COM with file transfer, I have the sockets class and the sockets library and some other stuff. Let me take a quick look. There's a diagram I want. Let's see if it's here. I want code. Project 3 help. Sockets. Yes. Class diagram. So this is what the sockets library looks like. There is an object called socket system that you declare once in your program. You have to declare it. If you're going to use any of these, you have to declare it. Now, you know, my library declares it. I'm sorry, the COM channel declares it, so you don't have to in your code. But if you want to use a socket system, you know, that isn't already been, you need to declare this. But you don't need to. So its constructor in this object, it only has a constructor and a destructor. The object calls WSA startup, the constructor calls WSA startup, and the destructor calls WSA shutdown. So you just declare it once, and when you're out of scope, you're done. Everything's cleaned up. This socket is what the listener returns from accept with. To this socket, we add a little functionality for the client to connect. And for the server, we add another little functionality for the socket listener to listen. Basically, this guy runs on his own thread, and that's already going in the library. And this guy expects to load a client handler that takes a callable object that tells him what to do, and that's what is talking. That callable object is what's talking to the client. So in our case, this callable object is just pulling framing messages out of the socket and dropping them in the queue. That's all he's doing. That queue is shared. Let's go back to that that model again. Let me pull up. So this queue is shared by all the client handlers. But unlike if you took SMA, we did that by making the queue static, which has a little annoying feature, but it's not static here. And that's because I have access to the stuff. I'm building the stuff that WCF hid from me. And so when I build it, the listener owns the socket, and he's just handing a reference to that. I'm sorry, the listener owns the blocking queue, and he's just handing, when he hands the socket to the client thread, he's also handing it a reference to that queue. And so all these clients have a reference to the same queue. Piece of cake. Okay. So now I can have two channels running in the same process without any funny sharing of unwanted sharing of the queues. Okay. There's a way to handle it in the C#, but we never talked about it. So this is what's called a single-threaded apartment. It works just like GUI application does, and this is important bearing for you. So what this means is that on the server side, when I pull messages out of the queue, only a single thread is pulling messages out of that queue. While I'm checking in, I got 3 clients that are all sending in files. Uh-oh, I'm going to have all kinds of conflicts. No, you're not, because one thread is going to pull out a message. Remember that file handling is happening before the message ever gets there. And now this client's going to pull out a message that says you got a file, and it's going to do something with the file. And then he'll pull out another message and do something with the other guy's file, and pull out a message. So no conflicts. Single-threaded apartment. That's a really nice model. If my goal was to squeeze every last available CPU cycle out of my server cores, I wouldn't do it that way. But I'm pretty close. I would gain 2 or 3 or 4% probably only going away from the single-threaded model, and I've avoided so many problems. Because here, as long as there are messages to pull out, that server's going to continue to be busy processing those messages, blah, 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 okay? So single-threaded apartment model, single thread is pulling, on the server side, is pulling messages out of that queue and processing them. And so now, in your project 3, you'll pull a message out of the queue and you'll put it in your dispatcher to call the right functionality. You'll just write a little dispatcher, piece of cake. Yes! Yes! And let's look at this interface a little bit. Let's go back and look at, let me pull up this interface. So I want to go and look at COM. So let's look at messages first. So here's messages. Here's message.h. So I have a key, a value, attribute, attributes, keys, blah, 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 blah. Endpoints. Endpoint is a combination of address and port number. And the address can be an IP address or it can be a network machine name. I have a machine, my main work machine at home is Odin. And so instead of saying 192.168.0.1 or .100 or whatever it is, I'll say Odin. And it works just fine. And the port is the port. So the endpoint, that 2 is an attribute that has the name, colon, port. It's the endpoint. And you know, I got a little code, a little struct that handles that for you. And I've got some attribute handling. So it's really easy. I can build an attribute naming the key and the value, add it to my message, or I can edit the value. I give it the attribute. I can edit its value. I can edit its key if I want to. I can ask you, do you contain this key? So, for example, I want to look for content length. Do you have the content length attribute? If you do, I know there's a file for me to pull out. Piece of cake. So I've got endpoint 2, 2 that returns an endpoint. I can have this 2. This is a attribute in my message that accepts an endpoint. I have a from that returns an endpoint and a from that accepts an endpoint. I have a name. I can give my messages names if I want. I have a command, which would be your ID. Check in, check out, 1, 2, 3, 4, 5. Or you could give it a name. You could call it check in, check out. But whatever you want. String file. So this is getting ready to do a file transfer. This is just saying I have this file that I'm going to send you. So it's file colon file name is the attribute. Okay. Content length. And I put in the size. Clear, I can clear the message. I can convert the message to a string, and I can extract a string from the message provided that it doesn't have binary bytes in it. I can even do it with a binary bytes, but I'll get some funny stuff here. So you really shouldn't do it with binary bytes. And I can show the message printed out. Let's look at COM. So, you can look at the interface at your leisure. So where did I put message? Oh, message passing com. Here it is. So here's com.h. So guess what? We said there was a receiver. Here it is. And when I call start, I give it a callable object that tells the listener what to do. And you won't change this. The listener is doing exactly what you need for project 3 and 4. You won't need to change that. But it's a way you can change it, what it does if you want to. And this starts a thread that the listener listens. So that listener is always running on its own thread. So that when the listener is blocked, that doesn't block the server. The listener is waiting for a connection. No connection's coming in. The server still runs just fine, thank you, because he's not blocked. It's the listener thread that blocks. And now I have get message. I have start, stop, and get message. That's it. That's the whole receiver. I can get the queue if I want, but almost never do you need to get at the queue. This really, my listener down below needs this. Okay, so, and I thought maybe someday I might need it. So I have a blocking queue, a receive queue. I have a socket listener, and this is a type. This is derived from socket listener. That's a socket listener type. And I have a receiver name. That's how I was printing out. You know, server is the receiver name, and client 1 was one client, client 2 is the other client's name. Here's my sender. Guess what? Starts the sender thread. I don't need to tell it anything because I'm not connecting yet. That thread starts up and blocks on the input queue. And then I say connect to that endpoint, and this creates creates a message that's just a connection message and sends it. And at the other end, I discard that message, okay, so that the server never sees that connect message. I just want them to receive genuine, you know, I don't want to have to say, oh, this is a connect message, throw it away. You can do it differently. And then post message. And if I want to send a file, I just configure my message to send a file. Okay. So if I'm going to send it in chunks, which I almost always want to do, you know, you could send, you could build a message that sent a 3 GB file. Let me tell you what happens. Windows sockets will throw the ugliest exception you ever saw in your life. Windows sockets don't handle that gracefully. In the old days, Windows sockets would send 500K, and that's all it would send. It would throw a nasty exception. 2 years later, it would send 2 megabytes, and then it would throw an ugly exception. Last time I tried, it would send 10 megabytes, and then it would throw an ugly exception. It's probably higher now. Somebody keeps increasing the buffer. You know, it's a static buffer. Come on, guys, you can do better than that. You're Microsoft. But that's what they do. So, so I chunk, always chunk. And I tend to use 2048 byte chunks. So for small files, it gets sent in one chunk. But if it's a big file, you see chunk, chunk. If you turn on the, you know, you do some logging, you'll see chunk, 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 chunk going down. Okay. But, you know, that means that your server has to do that. But I have a function in my COM that makes that easy for you. So now notice there's a private send file, blah, 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 blah. Now let's look at COM. Here's COM. You start COM, which just starts the receiver. You stop it. You post a message. You get a message and a string name. And I thought I did that here. I didn't do that here. I guess I did that in my CPP handler. But you could do a little send file function that just goes and builds the messages and keeps chunking out, you know. And you can take a look at, you know, take a look at my code and see how I'm doing it. In my code, in my demo code, I've got a function that does send file. It's not in the com channel, it's in a demo function. So with that, I'm going to stop. That's sockets. So the good news is sockets are simple. The bad news is sockets aren't really so simple. Okay. So there's a lot of stuff to put in place. And I think this COM with file transfer is a great, great vehicle to learn how that's all done. And if while you're looking at it to see how it's done, you find a bug, send me a bug report, okay? As far as I know, there's no bugs in it. I've used it a fair amount, and I don't know of any bugs. We used it last year, and people didn't have any problems. But if you find a bug, let me know. Right, Pei? Maybe. Okay, any questions before we break? Going once, going twice, we are out of here. Anybody that didn't get their midterm can see me at 2 o'clock. There was one person that saw me about was it you that saw me? No, it wasn't you. I did talk to you, but okay. All righty. See you all. I'll see you at 2, or I'll see you tomorrow, or if none of those, I'll see you on Tuesday.
真觉得它就是他发现你怎么变同时，太靠谱。这个习惯。但是现在回去